Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying functions lecture 1. In this lecture we'll be talking about basics of functions and VB curve method. So let us begin a lecture with the qualitative definition of function. So let's say we have a juicer over here and that is a very standard example every book uses, and we are giving inputs as fruits and we are getting output as juice, right? What do we mean by this? We are giving certain relevant inputs to the machinery and it is giving us outputs, desirable outputs, to be honest. Uh, Now we cannot give wood as input, we cannot give stone as input. These are irrelevant inputs. So basically that would lead to the concept of domain eventually, right? We have to give the desirable inputs, relevant inputs in the function to get the desirable outputs, right? This is the basic understanding of functions. Now let's talk about the technical definition of functions. Every element of A must have only one image in B and every element in A must be mapped. So these are the two key points in the definition of function. Let's say this is our set A and this is our set B and we are talking about the first one. We have this element A. So in case of relations, this was possible. This was possible in case of relations, but this is not possible in case of functions. We cannot do that. We cannot have two images with respect to A. We cannot have two images with respect to A. What we can have this kind of relation. Basically, this is allowed in functions. We can have two pre-images corresponding to one image, but we cannot have the other way around. We cannot have two images corresponding to one pre-image. This is not allowed. Okay. Now, what do we mean by this second one? Every element in A must be mapped. Now, if you remember, in case of relations, if this was set A, then we could do just this one. We could leave this one C element, and still we were still the definition of relation was satisfied, right? But in case of functions, this is not allowed. In case of functions, every element of A should have a mapping starting from there. It could be this way or it could be this way. Both ways it is fine, but every element of A must be mapped, right? Now, this would not affect anything, but there's a slight change in the implication of domain, codomain, and range. Slight change. Let's say this is a set A, this is a set B. In case of relations, if this was the case, if this was the relation, domain would have been A comma B, right? This would have been the domain. But in case of functions, we know that every element of A must be mapped. So this has to go somewhere, right? Every element of A would be mapped. So eventually, every element of A becomes a domain. So domain would be A comma B comma C, right? Now codomain is the same thing. Codomain is set B, that is 1 comma 2 comma 3, that is same as relations. And if we talk about range, in that case, again same definition. Only those elements which have been mapped come under the range part. So we are not considering 3 as a range, 1 and 2. So everything is same, only the implication of domain has changed. That basically means set A is the entire domain. The basic funda is the same, that all the elements of set A which have been mapped, and in case of relations there was a possibility that some elements are not mapped from A. So in that case domain would have been a subset of set A, but in this case domain would be would not be a subset. It's an improper subset actually. Okay. Now let's talk about inequalities and intervals, and we'll start that with brackets. Okay, so we have two types of brackets. We have curved ones and we have square ones. Okay, now we want to represent all the elements between 4 to 6, including both 4 and 6. In that case, we'll be using square brackets. And in case we want to represent all the elements between 4 and 6, excluding 4 and 6, in that case, we'll be using curved brackets. And let's say we have 4 to 6, all the elements from 4 to 6, but including 4 and excluding 6. In that case, we have square over here and curved bracket over here. So this is the basic notation, I think, which everyone should be knowing. Similarly, for the number line, open circles and filled or closed circles or closed, right? If you're if you know about this bracket notation, then definitely about this circle notation. What do we mean by that? Let's say we have to plot this one on a number line. This is 4, this is 6, These are the critical points over here. And when we say we have all the elements including 4 and 6 and between 4 and 6, then what we do, we put a closed circle over here, put a closed circle over here, and we draw like this. And let's say we have x greater than 5. So basically we mean that we have to include all the elements from 5 to infinity, right? If we have the greater than sign over here, we have not the greater than equals to sign over here. So that's why the curved bracket over here. If we have to plot this one, then what we'll be doing, this is our 5, and since we have an open bracket over here, we have a curve bracket over here. In that case, we'll be putting an open circle over here and doing like this. So basically this is going towards infinity, starting from 5 and not including 5. Okay, so this is the implication of open and filled or closed circles. Okay, so this was just a basic refresher about inequalities and intervals. Now let's talk about the most important topic of this lecture, that is wavy curve method. And we'll be starting with the building of intuition. Why? Because we cannot directly jump into the rules without understanding how those rules came. So let's start with a standard inequality, x minus 1, x minus 3, x minus 5, and x minus 7, let's say, greater than 0, right? And we have to understand the value of x it would take to satisfy this inequality. We have to understand, we have to find out the values of x for this inequality. For that, we'll be starting with plotting of number lines. So let's mark the critical points over here, 1, 3, 5, and 7 over here. Now let's take a case where x is greater than 7. We have considered these as zones. These all are zones over here. Okay. And we'll see how this function is behaving in these zones to understand. Okay. So let's take the first zone, that is x is greater than 7. So let's take x equals to 8 for the safer side. So the first term would become 7, second term would become 5, third term would become 3, and fourth term would become 1, right? Eventually, this is positive. We can conclude that if we take x greater than 7, in that case, whatever value we would put over here, x greater than 7, this would come out to be positive. Even if we take x equals to 7.01, this would become 6.01, this would become 4.01, this would become 2.01, this would become 0.01. Eventually, the product would be positive, right? So we can safely say that anything on the right side of 7 is positive, right? Excluding 7, definitely, because we have inequality over here and not greater than equals to 7. Okay, now let's take the second zone. We have 5 comma 7 over here. So let's say we have this, let's say x equals to 6. In that case, the first term would become 5, second term would become 3, third term would become 1, and fourth term would become minus 1. Now we have one single negative term over here, so that's why this would become negative. Now if we go with x equals to 4, basically over this, in this zone, that would give us 3 dot 1 dot minus 1 dot minus 3. Now we have two negative signs over here, so it would become positive. So we can see a pattern forming over here, plus minus, and we can extrapolate it over here. And you can just plot it and you'll see that it comes out like plus minus plus minus plus minus. Okay, but this is for this particular case. We cannot make a rule directly just based on one example, right? Let's say we have x minus 1, x minus 2, x minus 3 divided by x minus 5, let's say, and we have to solve this inequality. Now what? Now if you understand it clearly that x minus 5, if it is positive, it's going to affect the entire inequality positively. If it is negative, it's going to affect entire inequality negatively, right? If we have a minus 1, eventually for some value of x, if we have a minus 1 over here, that would make the entire sign of inequality as negative, considering that these all are positive, right? So that means we can treat it like a regular one. The number line for x minus 1, x minus 2, x minus 3, x minus 5, and for this one, the number line should be same, but here's the catch. We cannot have x equals to 5 over here. We cannot have, because in that case, denominator would become 0. So that is the only difference over here. Otherwise, everything is the same over here. So the number line would look like exactly the same. That is 1, 2, 3, and 5 over here, with the condition that x not equals to 5. Whatever the kind of values of x we are getting over here, we have to conclude that x is not equals to 5. Okay. Now that was the second point. Now let's say we have the inequality in the form x minus 1 greater than 6. Now here's the problem over here. Until now what we were dealing with x minus 1, x minus 5 greater than 0. So we had a 0 over here. So that's why we were able to differentiate between minus and plus directly. It was either minus or it was plus. But in this case we cannot do that. We have a 6 over here. Anything on the right side is also positive. Anything on the left side is positive or negative both. So we don't have that binary option over here. The binary option we had over here because of 0. Anything on the left side was negative, anything on the right side was positive. But in this case we have 6. Anything on the right side of 6 is positive, anything on the left side is negative and also positive. There are certain cases where it's negative, there are certain cases it's positive. So we don't have that binary case over here. So what do we do over here? We just convert that into the standard format. So let's open the bracket. That would give us x square minus 1, x square minus x minus 6 greater than 0. So that would become x minus 3, x plus 2 greater than 0. So this has become the standard format, and we can just plot it on the number line. This is minus 2 and this is 3. You can do plus minus plus. Okay. And you'll find out the zones. Now there can be case where we have inequality in the format 1 minus x, x minus 3, x minus 5 and x minus 7 greater than 0. Now let's mark the critical points. We have 1, 3, 5 and 7 over here. Now if we take the zones, the first zone is x is greater than 7. Let's say x equals to 8. In that case, the first term becomes minus 7. Second term becomes 5. Third term becomes 3. Fourth term becomes 1. Now, is it positive? No, it's not positive. It's actually negative. So, unlike other cases, the first zone is negative over here, and we know that zigzag pattern follows over here. So, the second zone would be positive. Third zone would be negative. This is positive. This is negative. But because of this we cannot form a proper rule. Initially it was plus minus, but as of now we have minus plus minus plus. So when do we use minus plus minus plus, or when do we use plus minus? There can be a little dilemma over here. So what do? We don't force ourselves into that dilemma. We just change this style into the regular style, right? We just change this format into the standard format. So we convert this into x minus 1 with a minus sign over here, x minus 3, x minus 5, x minus 7 greater than 0. Now this minus sign goes over there and changes the sign of inequality. So this becomes less than 0 over there. Now again this has become a standard format. If you plot the number line over here, you'll get plus minus plus minus plus. Okay. Now, until now, what we have studied is in case of rational inequality like this one, we have to follow the same rules, plus minus plus minus plus. In case of a regular inequality, we have to follow the same rule, plus minus plus minus plus. And in case of a different format, we have to convert that into the regular format and again plus minus plus. And in case of this kind of different format, we have to convert this into the standard format and do the plus minus plus minus plus. Right? So we have formed one specific rule that if we have this kind of standard format, regardless if we have a greater sign or less than sign over here, regardless of the sign, we are going to follow this particular pattern, and we'll see afterwards how to solve with the help of this particular pattern. But the pattern is plus minus plus minus plus minus in case we have written everything in the standard format, right? This has been established until now. Now moving forward, let's say we have a case where we have x minus 1, x minus 3 whole square, x minus 5, x minus 7 greater than 0. So how do we solve this one? Let's again plot the number line. We have 1, 3, 5 and 7 over here, and these are the zones we have. So the first zone is x is greater than 7. So basically let's say x equals to 8. In that case the first term would become 7, second term would become 5 square, third term would become 3, third and fourth term would become 1. And again we can see that this is positive. Now let's take the second case, second zone, where we have x belongs to 5 to 7, right? Let's say x equals to 6 over here. So the terms over here become, the first term would be 5, second term would be 3 square, third term would be 1, and fourth term would be minus 1. Again, we have a negative sign over here. So until now, the pattern has been following. Let's say we have the third zone, that is x belongs to 3 to 5. In that case, let's say x equals to 4. If x equals to 4, the first term is 3, second term is 1 square, third term is minus 1, fourth term is again minus 3. So we again have a positive sign over here. Now let's say if x belongs to 1, 2, 3, and let's say x equals to 2. In that case, this is 1 and this is minus 1 square, this is minus 3 and this is minus 5. Now this has become positive, this is positive, this is positive. Now we have a change over here. Until now we have been following plus minus plus minus plus minus, but over here we have a change, plus minus plus plus. Now what can we assess, or what kind of rule we can form with the help of this one? Anytime we have an even power over here, let's say we have an even power 2n, it can be 4, it can be 6, it can be 8, it can be anything, it can be even, it can be any even power, but it should be even power. Only in that case we'll be having this kind of rule. So whenever we have an even power over here on any term, in that case the critical point formed over here, and when we cross that critical point the sign doesn't change. We are crossing 3, 3 is formed from this element, and this element has an even power. So for any even power, whenever you are crossing the corresponding element, corresponding critical point, in that case sign doesn't change. Let me reiterate it once again. So whenever we have a term with an even power, so and whenever we are crossing a critical point corresponding to that element, in that case we are not going to change the sign. Okay. Now the point to ponder over here is this is applicable only for even powers. If we have odd powers on all the terms, it won't matter. That plus minus sign would follow as usual, right? But just in case we have a single term or multiple terms with even power, in that case we have to consider that rule, that whenever we are crossing an even power critical point, in that case we don't have to change the sign, right? Now let's try to summarize all the intuition what we have built until now and formulate them under two rules. So the first rule is standard format. So what do we mean by that? Any inequality should look like this one: x minus a, x minus b, x minus c, x minus divided by x minus d. So raised power e, f, g, and h, greater than, less than 0, whatever. Okay, but it should look like in this particular format. Okay, it shouldn't look like a minus x, x minus b, and divided by d minus x. It shouldn't look like this one. It should always in this particular format. These powers can be odd or even, be it doesn't matter, but it should have x minus a, x minus b, x minus c, and x minus d, and not b minus a minus x, b minus x, c minus x, that kind of format, right? That's the first thing. In case if we have something of that sort, what we saw earlier, greater than 6, in that case we have to convert that into the stand format. So given that any kind of inequality, we have to first convert that into this particular format. Only then we proceed with the plus minus format. Okay. Now the second rule is about even power. So let's say we have an inequality x minus a, x minus b raised power 2. In that case, whenever we are crossing that b point, b critical point, whenever we are crossing b critical point, the sign won't change. Sign won't change. So this is the second rule. If we have an even power on a particular term, so when drawing the plus minus thing, in that case, whenever we are crossing the B point, that is the critical point over here, having an even power, in that case, sign won't change. So plus would remain plus, minus would remain minus. So these are the two major rules summarizing the entire wavy curve theory. Okay. And now that we have understood the method, let's try to find out how to solve this particular inequality. Okay, so we know that we have this function, and this function is positive over here, negative over here, positive over here, negative over here, and positive over here. And we have to find out the zones or the values where this function is positive, right? So that basically means x belongs to this positive zone, that is minus infinity to 1, union this positive zone 3 to 5, union 7 to infinity this positive zone. So we have to take all the positive zones and take the union of that. And now let's say we have a less than equals to sign over here, let's say, and we have to solve this inequality. In that case, we have to find out the negative zones. In this case, x belongs to 1 to 2, but we have to take the square bracket over here because we have the less than equals to sign. Right? Union 3 to 5. But if you write 3 to 5 with a closed bracket or square bracket, this would be wrong because x cannot be 5. So we would have an open bracket over here. Everywhere will have a closed bracket or a square bracket, but in this case we have the curved bracket, open bracket, right? So this is how we have to solve the inequality. So the major thing is to form this particular number line or basically standardize this inequality. After that, it's a cakewalk. You just have to find out zones and take care of the basic domain restrictions. Now let's talk about domain of functions, and we won't be going too deep into discussion as of now because we haven't covered the types of functions yet. So once we're done with that, we'll be solving a lot more problems on domain. But as of now, we'll be just focusing on the rules of finding domain. Okay. So the first rule is expression under even root, that is square root, fourth root, etc., should be greater than equals to 0. So let's say we have a function x square minus 3. Now let's say x equals to 1. Now in that case, this function would become under root minus 2. That is not possible, right? Because that would be not real, that would be imaginary. In that case, x is not in domain. So what we have to do, we have to do x square minus 3 greater than equals to 0, because only those kind of inputs would be allowed inside a domain, inside a root, right? Even root. Now the second rule is denominator should not be equals to 0. So let's say we have a function x square minus 5 divided by x square minus 3. Now in this case x square minus 3 should not be 0. Why? Because denominator cannot be 0. In case if this function becomes 0, this entire function won't be defined, right? So in that case, we have to put this domain restriction that x square minus 3 should not be 0. So that is our second rule. Now let's talk about third rule. We have one function fx and the other function as gx. This one has domain d1, this one has domain d2. Now we are forming two functions. First function is h1x, that is fx plus gx, and the second function is h2x, that is fx dot gx. Now in both cases, final domain would be d1 intersection d2. Why? Let's say if some value of d1 satisfy this one, but it doesn't satisfy this one, and similarly for this one, some value of d2 satisfies this one but not this one. In that case, we have to take the intersection, basically the common values which are satisfying both this one and this one, right? So in both the cases, if we have fx plus gx and fx dot gx, we have to take d1 intersection d2. So that is the third rule. In case of fourth one, we have the rational function. So we have hx equals to fx by gx. Now in this case, there is one additional factor that gx should not be 0 and d1 intersection d2 is the same. So in this case as well, d1 intersection d2 holds, but gx should not be 0. That is the additional domain restriction. Otherwise, these two are more or less similar. Okay. So these are the four rules of finding domains of functions. And we'll be talking about domains, or basically we'll be solving more problems of domains once we are done with the types of functions. Okay. So this lecture was still here only, and in the next lecture, we'll be starting with types of functions. So let's meet in the next lecture. Thanks for watching.